Okay, so this is the last problem, problem 7, on our handout on related rates. That was handout 12. Please be sure to write down the solution in your notes. Okay, so what does the question say? The question reads like this. It says a kite 100 feet above the ground moves horizontally at a speed of 8 feet per second. And the question is, at what rate is the angle between the string and the ground decreasing when 200 feet of string has been let out? All right, so you should read that over a few times and try to get a picture of this kite 100 feet above the ground moving. And then we should probably underline the bits that seem to be most important. In particular, this kite sits 100 feet above the ground, and it's moving horizontally at a speed of 8 feet per second. All right, and the question is, at what rate is the angle between the string and the ground decreasing when 200 feet of string has been let out? So at what rate is the angle between the string and the ground changing? All right, well, as usual, we should try to draw a picture. And so let's do that. All right, so here we are. Let's see. Okay, so we've got this kite, like this. And let's draw the ground, I guess, over here. And let's say that the kite flyer is sitting here, and here we have the string. All right, so there's our string, and what do we know? If we go up here, we see, first of all, that the kite is sitting 100 feet above the ground, and it's moving horizontally at a speed of 8 feet per second. All right, so let's just try and put that on here. So it's 100 feet above the ground. So let me just complete this triangle here and note that this side of the triangle, in other words, the height of the kite above the ground, is 100 feet. So there it is. And let's look. What is our question? Our question is, let's look. Our question is, as this kite moves horizontally at this particular speed, at 8 feet per second, the question is, at what rate is the angle between the string and the ground decreasing when 200 feet of string has been let out? Okay, so what does that say? It says that first this kite is moving horizontally above the ground, so it's not moving up and it's not moving down, it's just moving horizontally, so in this direction here. And the question is, after 200 feet of string have been let out, at what rate is the angle, I can get it all in there, at what rate is the angle between the string and the ground decreasing? All right, so I think I understand the question, and it seems that there are some obvious variables that we need to introduce. In particular, we're interested in the rate at which the angle between the string and the ground is decreasing, so we better introduce a variable for that angle. So the angle between the string and the ground is this angle right here, so we'll call that theta. And our question is, at what rate is theta changing with respect to t? In other words, what is d theta dt when 200 feet of string has been let out? In other words, when this side of our triangle is 200 feet. Now, I'm not going to write 200 here, because notice that as time passes, because the kite is moving horizontally, the amount of string here is changing. So this is actually varying here, so it would be wrong to write 200 in my diagram here. This 100 is not changing, so I'm okay to write that. Okay, so we're going to introduce the variable theta for this angle, and I'll write that down in a moment. What else should I introduce as a variable? Well, it's a related rate, so we have to be given at least one other rate of change. And what is that rate of change? Well, we're told up here that the kite is moving horizontally at a speed of 8 feet per second. All right, so looking at our diagram right here, this kite is moving horizontally, so in this direction here, at a rate of 8 feet per second. All right, well, what is our variable? Well, this is a speed, and speed is the rate at which distance is changing with respect to time. So, what are we saying here? I could introduce any fixed distance. I could introduce a variable, rather, denoting horizontal distance of this kite from any point. So, for example, we might consider the distance then from the kite at any given instant to this point here, which sits 200 feet above, rather 100 feet above the kite flyer, and I could consider this distance from this point to the kite. And if I did that, then because the kite is moving at a speed of 8 feet per second, then if x were this distance right here, dx dt, the rate at which that distance is changing with respect to time, would be 8 feet per second. But it's not very natural to use this distance. It is, however, natural to use this distance here. The distance from this point, 100 feet above the kite flyer, to the kite is the same as this distance here, the distance from the kite flyer to this point right here that sits directly beneath the kite and on the ground. So we're going to let x be this distance here, the distance from the kite flyer to this point directly beneath the kite on the ground. And because we're told that the horizontal speed of the kite is 8 feet per second, I know that dx dt, the rate at which this distance is changing with respect to time, is 8 feet per second. All right, so let's write that down. Okay, so we're going to let theta equal the angle shown at time t, and we'll let x equal the distance shown at time t. Then, with these variables named, we can write down our question. Our question was, what is d theta dt? So our question is, let's write it down here. Our question is, what is d theta dt when, if you look up top, when, let's go up, make sure I got it right, when 200 feet of string has been let out. So when this length is 200 feet. All right, I'm not going to introduce a variable for it unless I have to, so I'll just write that statement in words. So we'll write that down here. When 200 feet of string has been let out. Has been let out. And what are we given? As we said above, we're given the speed at which the kite is moving horizontally. That was 8 feet per second, and that is the rate at which this distance x is changing, as we already said above. Okay, so we're given that dx dt is equal to 8 feet per second. All right, so we've written down our question in terms of our variable theta, what we're given in terms of our variable x, and now we need to somehow relate x and theta. All right, so let's write that down. So we need to relate x and theta. And to do that, we should look at our diagram. That's one of the main reasons we did the diagram. Okay, so here it is. Okay, so the question is, how can we relate this theta here to x? In other words, how can I relate this theta to this side, the length of this side of the triangle here, which is adjacent to theta, given that I know the length of the side that sits opposite to theta. So how do theta and the side adjacent and the side opposite to theta relate? Well, tan theta, you'll remember, is equal to opposite over adjacent. So tan theta is equal to 100 over x. So let's write that down. Okay, so here it is. Tan theta is equal to 100 over x. Okay, so now we have the theta and the x related. We know dx dt, and we're looking for d theta dt. What we should do now is differentiate. So remember, everything here is a function of time. As time passes, our angle theta changes. As time passes, our distance x changes, so we differentiate with respect to time. All right, and so first we're differentiating the tan theta, keeping in mind that theta is a function of time, so we're going to use the chain rule, differentiating the tan, the outer function. We have secant squared, leave the inner function, the theta, and then we have to multiply that by the derivative of the inner function, which is theta. We're doing that with respect to time, so d theta dt. Now on the right, what do we have? Well, you can use the quotient rule if you want, or you could view this as 100 times x to the minus 1. If you do that, the derivative is 100 times the derivative of x to the minus 1, so we'll have minus 100 times x to the minus 2. All right, so that is the derivative of the outer function. All right, so there's the derivative of the outer function. And now remember, x is a function of time. Just in case you don't see what I've done there, let me just write. I was thinking of this as 100 times x to the minus 1. Differentiating the outer function, I have minus 100 x to the minus 2. That's what we have so far. Now we have to differentiate the inside, that x, with respect to t. So times dx dt. All right, so this looks good. Let's go up, though, and see what is our question. Our question is, there it is, what's d theta dt when 200 feet of string has been let out? I know dx dt here, and I need d theta dt. Okay, so we're looking for d theta dt when 200 feet of string have been let out. So what are we going to need? I know dx dt, but I don't know x at the moment, and I don't know secant theta. Once we have secant theta and x, because we know dx dt, we'll be able to solve for d theta dt, which is what we want. So we need to figure out what is secant theta and what's x when 200 feet of string has been let out. So let's do that. All right, so we need secant theta and x when 200 feet of string is out. And for this, let's draw ourselves a picture. What does this picture up here look like when 200 feet of string has been let out? So I'm going to have a 200 here, and then from that I should be able to figure out what x is and also probably what secant theta is. So let's just draw a new diagram down here. Okay, so our diagram is going to look like this. We've let out 200 feet of string, and we have that this is 100. So the question is, how long is this side right here, the third side in this triangle? Well, by the Pythagorean theorem, that's going to be 200 squared minus 100 squared, and that is equal to root, I see I've got 100 squared common, 100 squared, and then I'm left with 2 squared minus 1 all squared, which is equal to 100 times root 3. All right, so the length of this side here is 100 root 3. That gives me our x in this case. So x is 100 root 3 when 200 feet of string has been let out. We also need secant of theta when 200 feet of string has been let out. So let's see. This is fine. We know all three sides of this triangle, the lengths of all three sides of the triangle, so we could figure out any trigonometric function at theta. In particular, what's secant theta? Secant theta is equal to, well, it's 1 over cosine of theta. And cosine theta is equal to adjacent over hypotenuse. So we have 1 over adjacent over hypotenuse. That's hypotenuse over adjacent, which is to say the hypotenuse is 200 over the adjacent, which is 100 over root 3. So this is equal to 200 divided by 100 over root 3, which is just 2 over root 3. So now we have what we needed. We have secant theta, there it is, and we have x, there it is, when 200 feet of string has been let out. So now what are we going to do? Well, we're just going to substitute into what we'll call star, which is to say we're going to substitute into this one right here. All right, so we're going to replace secant theta with what it is. We just found that out. X by what it is. We just discovered what that is. We know what dx dt is, so we can replace that by what it is. If we look up above, we'll see it. There it is. dx dt is 8 feet per second, so we'll replace that dx dt down here by 8. And if we do that, well, we'll be able to solve for d theta dt, which, if you go up again, is exactly what we are trying to find, d theta dt when 200 feet of string has been let out. Okay, so let's substitute into star. And what will we have? We will have, so we'll have secant squared theta, and this is what secant theta is. So we'll have 2 over root 3 all squared times d theta dt, so I'm just substituting into that star that we had up above, is equal to minus 100 over x squared. So minus 100, I had it written up there as minus 100 times x to the minus 2, which is minus 100 over x squared. What's x? X is 100 root 3 at this moment, all squared, and times dx dt, which we noted already is 8 feet per second. All right, so this looks good. Now we can solve for d theta dt. d theta dt is going to equal, well, here I have 4 thirds, and so multiplying both sides by 3/4, I'll have 3 quarters over here times, we've got a 100 here, you can cancel with one of these hundreds down here. I've got that negative, so maybe I'll put that negative out in front. So negative and 1 over, canceling one of the 100s, I'm left with 1 100. I still have that times 3 and times 8. And now, canceling the 3's and the 4 with the 8, we'll have minus 2 over 100. And this is equal to minus 1 over 50, and this is the rate at which that angle theta is changing. So this is measured in radians, and this is per second. Okay, so what this says then is that the angle theta is changing at a rate of 1 over 50 radians per second, and because we have this negative here, this means that theta is actually decreasing at a rate of 1 over 50 radians per second. So let's just say that for our final sentence, for our final statement. When 200 feet of string has been let out, theta is decreasing at a rate of 1 over 50 radians per second. And note that because we've said that theta is decreasing already, we can write 1 over 50 here. We don't have to include that negative. All right, so there we're done. Maybe we should just go up to the top to see if it makes sense to us that theta would actually be decreasing. So going right up to our original diagram. Does it make sense that this theta is decreasing? And yes, it does. Kite's moving in this direction here. As the kite moves in this direction here, this angle theta is going to decrease. So you can see it decreasing. This certainly makes sense. So we are done.